I'm going to talk about neutron stars today. There are a lot of relation with neutrino physics, as I'll describe a little bit at the end. But it's mostly about very dense, very cold matter. So I'll start talking about just give you a rough idea of what neutron stars are and how they relate to the Qcd phase diagram. Then I'll talk about some of the calculations that we do. That includes starting with interactions between nucleons. It's very important for the structure of neutron stars, and how we calculate the equation of state using quantum Monte Carlo methods. There's sort of two regimes which are interesting. One is the very low density regime. There you have analogs to experiments in cold atom physics and other related systems which you can use to experimentally test your theories of strongly interacting matter. And then the main part of the mass-radius relation of neutron stars comes from the high-density equation of state. There are observations, but there are limited laboratory experiments. I'll describe some of the constraints coming from both. Of course, real neutron stars are not just neutrons. They certainly have protons in it. Maybe they have hyperons. There's been some very interesting recent work on that, and I'll describe some of that. And then the mass-radius relations and observations from neutron stars. So how well do our theories of dense matter correspond to what we see observationally? And then at the end, I'll mention something about neutrinos, and in particular about neutron star cooling. It involves many of the same ingredients that go into the equation of state, including the energy gained by adding a few protons, superfluidity in the neutron star, and related topics. This work has been done with Stefano Gandolfi at Los Alamos, Alex Gazerlis, who's now at Guelph, Diego Lanardoni and Alessandro Lovato, who are at Argonne, and Sanjay Reddy, who's at UW and the INT. So this is the simplest possible picture of a neutron star. There's an outer crust which has ions and electrons only, so basically nuclei and electrons. Then there's the inner crust. The density gets higher, and some of the neutrons start to leak out, and so you have electrons, neutrons, and nuclei. You have very big, very neutron-rich nuclei with a neutron gas in between. And of course, the electrons are nearly uniformly distributed since the mass is so light. The main bulk of what I'm going to talk about is the core. There's a neutron-proton Fermi liquid, actually with superfluidity. And there's a few percent protons, and to maintain charge neutrality, there's a few percent electrons that goes with that. So a neutron star is about 1 to 2 solar masses. The radius, as I'll show you, is around 12 kilometers, plus or minus of order 2 or 3. This was amazingly predicted within about 1 year after the discovery of the neutron. There's a neutron star, basically, it's mostly neutrons because you want to have charge neutrality. Electrons, since they have a low mass, have a very high Fermi energy, and you don't want to have too many electrons or protons, so you have almost all neutrons. In the interior, we don't really know what's happening. There's a possibility of a transition to quark matter. That has been discussed in many contexts. I'll talk about that a little bit later on. So the structure of the neutron star is primarily determined, or basically determined, by the Qcd phase diagram. This is a schematic picture I took from FAIR, which is a new facility, heavy ion facility, among other things, in Darmstadt. It's under construction. So this axis is temperature in MeV, and this is net baryon density, or chemical potential. So nuclei on this scale are around here. Density of essentially saturation density. All nuclei have more or less the same density. RIC and the LHC, in the heavy ion collisions, the two nuclei are going through each other so quickly that there's essentially no net baryon density left, very small in any case. So they're going up close to this axis. And Rick is talking about doing some energy scans, lowering the energy and trying to reach this critical point. This actually is not a phase transition here. This is a crossover. But what we're going to talk about here is sort of the opposite end, very high baryon density. So nuclei are neutron stars. Neutron stars go up to a few times the density of nuclei, and they're mostly neutrons, as I said. Off very far to the right, asymptotically to the right, we know, there's a question mark here, but actually we know theoretically that there is a color superconductor. So we know that matter, if you get it dense and cold enough, will go to quark matter, where you have basically superfluid quarks with coupling between the quarks to make a superconductor. There are many proposed phase diagrams which have more variety of different superfluid pairing mechanisms in this regime. So we know it goes to color superconductor eventually, but we don't know where. And in particularly, we don't know exactly where neutron stars are on this diagram. Of course, the neutron star has less dense on the outside and more dense as you go to the interior. We don't know how much that interior, or if the interior is dense enough to reach this color superconducting phase. The other new thing that's very important, which happened only in 2010, and now there's another example, was an observation of a 2 solar mass neutron star. So this is a different kind of plot here. Here I plot the radius of the neutron stars in kilometer, and here's the mass of the neutron star. For a very long time, almost all masses were between about up to 1.5 or 1.6 solar masses. These lines here on the curve are various possible equations of state. So what is the energy at zero temperature energy of matter as a function of density? And as I'll describe, how does that translate into a mass radius relation? So if you make a heavier neutron star, there are a whole variety of different models. Almost anything can happen. And a lot of these very soft equations of state, either in nucleon degrees of freedom, which are some of these curves here, or these are sort of quark matter predictions. But these are basically, if they don't reach up to this 2 solar mass neutron star, since we observed one, they're now ruled out. There's still a huge number of possible equations of state. This is another quark matter one. All these curves here are various relativistic mean field theories of dense matter. And these curves here are essentially based on nucleon-nucleon interaction. That's basically the ones I'll be talking about, fall into sort of this kind of regime. So this doesn't show up terribly well, but it's basically saying that we know the interaction between nucleons extremely well. There are thousands of data points. These have been fit with various kinds of models of the nucleon-nucleon interaction. The most important one for neutron stars is the singlet S0. So it's 2 neutrons paired to spin 0 in a relative S-wave state. The fact that it's very large and positive here means the neutrons attract each other and they almost form a bound state. There's a scattering length of minus 18 Fermis, which is very large in magnitude on a scale of nuclear physics. So that's why it's related to studies of cold atom physics, where you can basically tune the interaction to get any interaction strength you want. As you go up to very high density, the phase shift crosses 0, which means it's getting more and more repulsive. And that's what's supplying a lot of the pressure to allow heavy neutron stars. And the singlet S0 phase is very large, both attractive and then repulsive. As I said, it dominates a lot of the physics that's going on, except for some of the superfluid physics where the P-wave stuff also matters. So if you just take a density of around 2 times saturation density, so normal nuclei have 0.16 nucleons per Fermi cubed. Typical density more in the interior of a neutron star would be about twice that. So the Fermi momentum for that, if you just calculate it, is 2 inverse Fermi. That means that the center of mass energy is about 160 MeV, and the lab energy, if you're comparing it to a scattering experiment where you have neutrons and protons scattering, that would be about a 320 MeV. So that's somewhere around the middle of these plots. So you have to study the phase shifts up to fairly high energy to be able to predict what happens at densities of, say, 2 times saturation density. Sure.
What's that one that was in the bottom middle that looks like it's so far off from?
Yeah, that's a triplet D2. This is a very simplified model of the nucleon-nucleon interaction. So in this particular model, it's a little too restricted, and you can't fit that with this particular form. There are more sophisticated forms that do a better job on that. Yeah, so basically the ones that matter a lot are the singlet S naught. Not all of these phases are available to 2 neutrons. Because you have identical particles, you have to have anti-symmetry in the combination of spin and space. So you have singlet S naught is important for neutrons, and the triplet P naught, triplet P1, and triplet P2 are also quite important for neutrons. Okay, so this is the connection that I mentioned between dense matter and cold atom physics. Actually, George Birch proposed this simple kind of interaction, an attractive interaction with 0 range, as a model of low-density neutron matter. As I said, the neutron-neutron scattering length is basically the 0 energy phase shift here, how the phase shift approaches 0 at 0 energy is minus 18 Fermis. There's very strong attraction at low energy between the spin up and spin down neutron. In cold atoms, cold Fermi atoms, people like Ketterle have been working on studying the phases of matter where these things are atoms. So you have 2 species of atoms, which we'll just call spin up and spin down. They're antisymmetric. Use a Feshbach interaction to make this interaction, which is very short range compared to the distance between the atoms. And they can study the equation of state and so forth. This particular plot here shows the energy, or the potential energy, if you take one of these models that's fit to these phase shifts, as a function of the separation between the nucleons. So the central, or the average overall spin and isospins, is this solid line here. So it's extremely repulsive at short distances. That's because of this phase shift out here, which is at high energy is negative. And then there's an intermediate range attraction, and then at long range, there's basically 1 pion attraction. So at very low energies, all you see is some combination of this, and you get this very long scattering length. But these models have pion exchange at long distances. They have some form of 2 pion exchange, which gives some intermediate range attraction. And then as the 2 nucleons are right on top of each other, it gives a very strong repulsion. And it's that short range repulsion and the spin-dependent nature of the interaction which gives you the saturation or supplies the pressure to keep 2 solar mass neutron star from collapsing into a black hole. So the real models of the interaction are very complicated in a sense. It's not like a simple Coulomb interaction, or it involves not only the spatial separation between the nucleons, but it involves their spins, their isospins, so whether it's 2 neutrons or a neutron and a proton. And it involves the angular momentum, so spin orbit type effects. And we're just trying to solve for the 0 temperature limit of a system with such an interaction. So we're just trying to solve the Schrodinger equation. In principle, it's very simple to write down. But the Schrodinger equation has a huge number of components, each describing different possible spin and isospin combinations of the nucleons. So typically, when we do a simulation, we have about 60 to 100 neutrons. If you take 66 neutrons and put in periodic boundary conditions, which is a typical simulation for neutron matter. 2 to the A, which is the number of possible spin states, each spin up or down, is almost 10 to the 20th. So we have to use Monte Carlo methods to solve for this Schrodinger equation. And there are similar methods that can solve for finite temperature properties of the system. So we use quantum Monte Carlo methods to study these. And the particular method I'll describe is auxiliary field diffusion Monte Carlo. There's a variety of these things which might make slightly different choices about what you sum over or integrate explicitly and what you use Monte Carlo to integrate. But basically, we're trying to project out of a trial function down to the zero energy state. So we take our best possible guess for the system here. We evolve it and cool it. So this operator will just remove any high energy excitations that are in this trial state, and we get the ground state. The same type of method, if you just take the density matrix instead of the wave function here, will give you a finite temperature ensemble and the partition function, which you can use to sample observables. Of course, this operator here, e to the minus h tau, you don't know, because in order to know that, you'd have to know all the excited states of the system or all the states of the system. But we can sample it by taking a high temperature expansion for this. So a short value for tau corresponds to high temperatures. And then we just iterate it. So we take something like this, and we iterate it in terms of a branching random walk many, many times. And this operator here has e to the minus v tau over 2. That's just the potential energy. So that says whenever the two nucleons are nearly on top of each other and the repulsion, the potential is very large and repulsive, that reduces the strength in that particular region. When the potential is attractive, it makes a larger strength. This kinetic energy, if you take non-relativistic kinetic energy, it's just p squared over 2m. So this is a Gaussian in momentum. To Fourier transform that, it's a Gaussian in coordinate space. So this either increases or decreases the strength at a particular point in configuration space. This just diffuses the particles around in coordinate space. And this again, you just take a symmetrized way of writing this to increase the accuracy of your expansion here. This doesn't really solve the problem for nuclear physics. If you take liquid helium or atomic physics where these are electrons, this is just a number. The potential is just a number. But as I said, for nuclear physics, there's all kinds of spin and isospin dependent potential terms. So you have to do something here. For light nuclei, you can just sum over all the spin and isospin states and just use the Monte Carlo only in the coordinates of the particles. But if you want to do something like neutron matter, you have to sample over the spins as well. And for larger nuclei, you'd have to sample over the isospins. So you use auxiliary field techniques. These are used a lot in condensed matter, particle physics, basically any kind of physics. You can't evaluate this thing. Sigma I dot sigma j is a matrix in spin space. So you have 4 initial possibilities for the 2 spins and 4 final possibilities. So this is a matrix. But what you can do is to sample insert auxiliary fields and sample them. So you take matrix elements that look like this, couple this spin to an auxiliary field, couple the other spin to an auxiliary field, and you can sample using Monte Carlo this auxiliary field. The linear term here will drop out because you're summing x equals plus minus 1. But the quadratic term, which gives you a linear in x here and a linear in x here, those will be correlated and they'll work out to give you the right expectation value of the full potential. So you have a fluctuating mean field x, which you use to do the Monte Carlo simulations. So the nuclear physics simulations is a branching random walk. The random walk is in the 3A spatial coordinates of the particles, and also the spins and isospins of each of the nucleons. So at each step, the spins start up. If you take a very simple model, you have half spin-up neutrons and half spin-down neutrons in just plain waves. That's the simplest possible model. But as your sampling goes along, they move in space, and the spins for neutron matter rotate. So instead of having all spin up, half spin up and half spin down, you'll have each nucleon having a linear combination of spin up and spin down. And the correlations between those are encoded in the phase relationship between those spins of each nucleon. So that's basically all I'm going to say about the simulation. I'm very happy to answer questions or talk to you later about that. These can be very large simulations. The neutron matter is not so bad because it's only neutrons. But if you want to explicitly sum all the spins and isospins and look at things like Hoyle states in carbon-12, these go on Mira and require tens of millions of core hours to do this simulation. And you can then look at a lot of interesting discrete transitions in nuclear physics. Okay, so here's the equation of state that you get. I said that neutron matter is very similar to fermions with the zero range interaction. On this axis, I plot the equation of state. I've divided by the free Fermi gas energy. So at zero density, of course, it's just a free Fermi gas. Analytically, due to work of Li and Yang, you know how that behaves as a function of the density. Here, I've plotted the Fermi momentum times the scattering length with the minus sign. So this is zero density. This is increasing density to the right. And at very low density, the energy decreases as you increase the density because they're closer together and the interaction can do something. Cold atoms at unitarity, they adjust this parameter all the way to infinity, but it's a smooth transition in 1 over KFA, so it's actually not so different from this point here of KFA equals 10. Cold atoms have zero effective range, so if you do an expansion of the S matrix, you have the scattering length is the first term and the effective range is the next term. It's basically something to do with the range of the interaction between neutrons. In cold atoms, that's typically very small. There are cases which they can study with a finite effective range. Neutrons, however, have a finite effective range. They have a fixed scattering length. It's just fixed by the nucleon-nucleon interaction, but you can change KFA by changing the density. But as opposed to cold atoms, there's an effective range which is of order of 10% of the scattering length. So that makes some difference. And if you did cold atoms with the same effective range, you get this. And eventually, neutrons, which are these red and green points, diverge a little bit from this because even higher order terms in the nucleon-nucleon interaction become important. The other thing which I'll mention briefly is both of these systems, low density neutrons and cold atoms, are very strongly superfluid. This comes in later when we want to talk about neutrino propagation in dense matter. The superfluid gap is so strong in unitary fermions that if you put the system in a trap, so that would be some harmonic potential that the spin up and spin down atoms are sitting in. If you put more spin ups and spin downs, they don't mix. And it costs so much energy to add an extra particle and as opposed to a pair in the interior where the density is high. The extra particles prefer to sit out in the exterior of the trap. And in fact, so if you take an even odd kind of mass difference, if you look at a system with even number of atoms or neutrons with equal up and down, you get a certain energy. If you add only one, this is the energy of that extra particle as a function of its momentum. So in a normal superfluid, this would have a minimum right at the Fermi surface here of 1. Because the interaction is so strong here, it starts to move in. As you make the interaction stronger and stronger, these fermions couple into bosons, tightly bound bosons. And then in that limit, the minimum is actually at k equals 0. So unitary fermions, which have this interaction adjusted basically to give a zero energy bound state, have a minimum somewhere in the middle. But the striking thing is it's a superfluid gap, is about half the Fermi energy. So at an electron superconductor, this is like 10 to the minus 3 or something. So it's a tiny effect. Here it's huge. Neutrons is not quite as big as that, but it's still very large. This is a plot of that gap as a function of KFA. And here you can see the cold atoms are up here. Neutrons are not so large, but they're still of order 0.3 times the Fermi energy. So it's a huge gap. It's very strongly superfluid. Another thing that's important in neutron matter and neutron stars is that higher densities, this particular S-wave gap will close. The system is not, it becomes repulsive at higher densities, as I showed, and so the not superfluid in S waves. But it's thought very likely it's superfluid in P waves, triplet P2, triplet F2 coupled channels in particular, and that affects the cooling of the star. So these are the quantum Monte Carlo results, these points. The black lines are just very simple BCS mean field theory. This has been studied experimentally in cold atoms, and so we believe these calculations should be accurate to something like 10%. But at higher densities, you really can't make a comparison with cold atoms anymore. And when you go up to nuclear density, the effective range is a very similar length to the average distance between particles. So you have to look at what phenomenological information or experimental information is available. So if you look at the equation of state of dense matter, you know basically from the binding energy of nuclei, it fits to those, that the density of nuclei is on average 0.16 nucleons per cubic Fermi, and the energy, this is removing the Coulomb, is minus 16 MeV per nucleon. So real nuclei are bound by about 8 MeV per nucleon, but it's the changing the Coulomb that brings you down to minus 16. This is just from the strong interaction. Neutron matter, though, is never bound, except gravitationally, of course. And this is the neutron matter equation state is somewhat reduced from the free Fermi gas at low densities, and then it picks up and is quite a bit more repulsive than the free Fermi gas at higher density. So the only thing that's really directly accessible to you is this point here, but you can get some information on the symmetry energy by studying things like neutron-rich nuclei and try to understand the difference between equal number of neutrons and protons in a pure neutron system. And this will make a big impact on, knowing this precisely would make a big impact on our knowledge of neutron stars. So the interaction, not only is the two nucleon interaction important as you get to higher densities, but since nucleons are not point particles, they have very low-lying or fairly low-lying excitations. For example, delta resonance at about 300 MeV. You can excite that in an intermediate state, and these three nucleon forces start to make a role. You can calibrate those in studies of light nuclei, as has been done here for one particular model of the interaction. And so you have some idea about the strength of these three nucleon forces. They're roughly on the order of 10% of the strength of the nucleon-nucleon force. So they're not huge effects, but they can be important in the equation of state, particularly at higher densities relevant for neutron stars. So what we've done is taken a whole bunch of models of this three nucleon force and fix the symmetry energy. So we're going to pretend that we know the energy of neutron matter at saturation density, so at the same density as nuclei, exactly. We know the energy of nuclear matter is about minus 16 MeV per nucleon, and so this is saying that the energy of neutron matter at that same density is roughly plus 17 MeV or 18 MeV in this particular choice. And these different curves are just different three nucleon forces of all different kinds, which are adjusted to give that same value of the symmetry energy. So they have to agree at this point. Down here at low density, the three body forces doesn't matter much at all, so they basically still look like all on the same curve. As you extrapolate up to higher and higher density, they do start to diverge a little bit. This is twice nuclear matter density, and this is 3 times nuclear matter density. So it's significant up here, but it's still not a huge uncertainty. If you do the same thing but assume different values of this symmetry energy, you get the following curves. The red curve is just from the 2 nucleon interactions alone. That's, as has been known for a long time, too attractive or too soft at high density. The black is a very strong repulsive 3 nucleon interaction. And these bands here are for these 2 values of the symmetry energy. If you made different 3-body forces with these black and red symmetry energies, you'd get a bands here and here as well. So the main uncertainty, if you could pin down the symmetry energy or exactly what the energy of neutron matter is here, you could make a really pretty strong constraint on what happens as you go to higher density, at least assuming you don't have any exotic physics happening, like transitions to quark matter or hyperons or other things coming in. What's particularly striking, if you look at in detail around this density here, is that fixing the symmetry energy places a very tight constraint on the slope. It's kind of the same thing as I was just saying earlier. If you pick the value of the energy here, you know, because the 3-body force doesn't basically do anything down here, more or less exactly the slope. And that's shown in this curve here. So we plot the symmetry energy, the difference between nuclear matter and neutron matter for different suggested values, and on the vertical axis we plot its slope. And so there's an extremely tight constraint. These are for all different kinds of models of the nucleon-nucleon interaction and of the 3 nucleon interaction. So you see you have a very tight constraint. It's this constraint that allows you to make very accurate predictions of what happens at least up to of order 2x saturation density. There's new interaction models based on chiral interactions and effective field theories. They give essentially exactly the same kind of result. This is what we know from fitting nuclear masses. So nuclei have, of course, a bunch of different ratios of neutrons to protons. Typically, as you get to heavier nuclei, because of the Coulomb, you start getting more neutrons. And this is the same L over S plot, just from a variety of mean field fits to the masses of all the nuclei. And there's some uncertainty band. So the curve I showed before sort of started at 30 and went up here. But you can fit nuclear masses and get a very strong correlation between L and S from that as well. You can then look at a whole bunch of different experimental observables in nuclear physics and try to make this same kind of constraint. These nuclear masses, that's the curve of the previous figure, is this yellow band here. These blue bands are from the theory, from our calculations. They actually have probably some of the tightest constraints. If you want to get constraints in the other direction, sort of minimize the uncertainty here, right now this is only partially successful, but they're looking at lead dipole polarizability, neutron skin of tin, and there's experiments looking at lead and calcium where they do parity violating electron scattering and look at the difference between the neutron and proton distributions in something like lead or calcium-48. And that puts strong constraints as well. In this particular plot, they use neutron stars to get this hatched band. I'll discuss that right now. So basically, if we go from the equation of state, or the energy per particle, as a function of density, you just use the Tolman-Oppenheimer-Volkoff equation, which from 1939, which is basically a GR equation, equating the pressure. You go from the equation of state to the mass as a function of radius. So if you have the pressure here, you can see at low densities, you have low pressure. The mass of the neutron star is very small, and the radius can be very big. But as you add more and more mass, the radius contracts. And depending upon the shape of your equation of state, you can get all those different shaped curves I showed before. But typically, modern equations of state, they're very attractive because basically neutrons are attractive at low density. So they come in nearly horizontally until you get up to close to 1 solar mass of neutron star, and then they tend to rise vertically. The pressure is building very rapidly here. You're transitioning from the attractive interaction to the very repulsive interaction. And then they'll have some kind of maximum mass. We know that maximum mass has to be at least of order 2 solar masses now. So that constrains this to be very repulsive at high densities. A lot of pressure, and that's holding up the neutron star and allowing it to exist up to 2 solar masses and not collapse to a black hole. If you just use, as a contrast, if you just use free Fermi gas of neutrons, so totally ignore the interaction between the neutrons, you'd get an upper bound of about 0.7 solar masses, and that's what they did in 1939. So you're not way off of that, but you're off by a factor of 2 or 3. So if you take these equations of state that I showed before, here you can then turn those into mass-radius relations using the Tolman-Oppenheimer-Volkoff equation, and you get these mass-radius relations. So this is the radius in kilometer. This is the solar mass of the neutron star. This is 2 nucleon interactions alone, so pretty attractive. These are the green and blue bands, which have somewhat higher symmetry energies. This black band had the highest symmetry energy. Almost all neutron stars we know are somewhere around 1.4, 1.5 solar masses. So if you had a 1.4 solar mass neutron star, these curves would tell you, depending on the equation of state, that the mass would be, say, 11 kilometers or 12 kilometers. Now we know that there's also a 2 solar mass neutron star. We don't know its radius. If we knew one neutron star, its mass and its radius very precisely, we'd have very tight constraints on the equation of state of dense matter. And that's one of the goals of this kind of research. There has been a lot of progress in that, but it's still somewhat controversial. So this are trying to look at observations of neutron stars and the mass and radius. There's in this particular paper, Andrew Steiner, Jim Latimer, and Brown from 2010 looked at 3 X-ray, that should be bursters, and 3 low-mass X-ray binaries. And from looking at those observations, and for the bursters using Eddington luminosity, they can place constraints on the mass and the radius. In some cases, they're very specific. In some cases, there's big uncertainties. If you look at these individual stars, as I said, there's a lot of controversy involved in this because of the atmosphere of neutron stars and how they might affect your observations. But what they did is then combine these data for individual stars into an overall plot. There's still some uncertainty on the left. It's making one assumption about these atmospheres, and on the right it's making a different assumption. But they get this overall constraint. If you assume that all neutron stars are made up of the same kind of material, in other words, they do reach some kind of equilibrium, then all of them should lie on one curve. And depending on the astrophysical assumptions you make, it's either this curve or this curve. But this is actually a fairly tight constraint for 1.4 solar mass neutron stars. It's somewhere between 11 and 12.5 kilometers, something like that. So we can compare those observations to the calculations based on nucleon-nucleon interactions, and we actually get quite good agreement. The green and the blue bands here are the ones with slightly different symmetry energies. Those are the calculations, and these observations, they have to assume something about what's happening at high density. Black and red are some kind of assumption of quark matter, and red is just sort of arbitrary polynomials. But they're all adjusted. What's make this actually work is that you know that it has to go to a 2 solar mass neutron star. So they get fairly tight uncertainties now. And they say that the symmetry energy is between 32 and 34 MeV, and its slope is between 43 and 52 MeV. One of the things that people are looking forward to is observations of neutron star binaries collapsing, and they're emitting gravitational waves. That will also tell you a lot about the equation of state. And it won't be subject to a lot of the same uncertainties, astrophysical uncertainties, that the observations currently require. This is a very simple picture that I presented to you. It says nothing about protons. It doesn't say, what about hyperons? A lot of people think that hyperons have to occur in neutron stars. I don't think that's so clear. Anyway, this is just some recent work on some of those topics. All the calculations I've shown basically assume there's some quadratic dependence on the energy. So it's pure neutron matter is over here. This is dying, but over here to the left, this is number of neutrons equal number of protons. And they assume some quadratic dependence. So Stefano Gandolfi and collaborators have recently done some calculations of this and confirmed this quadratic dependence in microscopic calculations to pretty high accuracy. So that seems fairly well under control. The thing that is much more uncertain is what happens if you had hyperons or strange baryons into matter. So we know hyperons are bound in nuclei, typically of order 20 MeV or so. If you extrapolate it out to matter, a hyperon in a normal nucleus would be bound by 30 MeV. Of course, it's unstable because a hyperon is a couple hundred MeV heavier than the nucleon, so it decays very rapidly. But it lives long enough that you can extract a binding energy. That binding energy is significant on the scale of the mass difference between the hyperon and the nucleon. And so if you do simple models of the hyperon-nucleon interaction and you fit this 30 MeV binding energy, you find out that way before any of the stuff I talked about high-density neutron matter, that hyperons will appear in a neutron star. And they'll bring the pressure way down, and they will not let you get anywhere near a 2 solar mass neutron star. But if you do a more sophisticated treatment, which includes 3 nucleon forces, hyperon, nucleon, nucleon, we know those are important just because like a nucleon has an excited state of a delta at 300 MeV, the lambda has an excited state, the sigma, at only 80 MeV. So those 3 body forces are very important. If you look at the spectra of light hypernuclei, you also see they're very important. And that 3 body force, if you fit all the hyperon hypernuclei that are known, pushes up this density where hyperons start appearing, depending upon the exact model, either to 3 times or even higher normal saturation density. So this work, which has just been shown in the archive, is saying that microscopic calculations may say that hyperons basically don't appear in neutron stars except for maybe in the very central region where they wouldn't play too big of a role in the mass-radius relation. Okay, I will spend the last few minutes talking about neutron star cooling. The biggest relevance for neutrinos in neutron stars for cooling, especially when they're hot. Of course, the protoneutron star in a supernova cools primarily by neutrino emission. There you want to know things like what's the initial, as the neutrinos escape from the protoneutron star, what's the distribution in energy of the different flavors and neutrinos and antineutrinos. There's a lot of models for that. I think more sophisticated models might be very valuable in constraining some of that information. But as the neutron star cools further, it still, for the first 100 years or so, cools primarily by neutrino emission, because the neutrinos can escape from anywhere in the neutron star, and that allows much faster cooling than just cooling through photons at the surface until the neutron star gets pretty old. So there are constraints and measurements of neutron star cooling. This is temperature on the vertical axis and time on the horizontal axis here. For a variety of neutron stars, you can see there's not a universal behavior here. Some of these are just limits, so if they have an arrow only pointing down, that means it's just the temperature is lower than that point. But some are actual values with error bars, and they seem to indicate that not everything is a unique value, a unique curve of temperature versus time. That's okay, of course, okay, because neutron stars can have different masses and different densities, and so different processes can dominate. So Latimer, Pethek, Prakash were some of the early ones to study that should be direct Urca process, where you have a neutron going to a proton, electron, and anti-electron neutrino, and then subsequently this proton combines with an electron to give a neutron and electron neutrino. This process can only go at high densities. If you assume that the interactions are not terribly important, but all these, at zero temperature, all these processes have to be essentially at the Fermi surface. So the neutron momentum, the proton momentum, and electron have to be essentially at the Fermi surface. That says that this can only happen at high densities and at fairly high proton fractions, so about 15% proton fraction. Exactly where it can happen depends a lot on the equation of state, in particular on what happens as you add protons to neutron matter. So this is a subject of quite a bit of study. This mechanism is extremely fast. It's just basically a one-body process, right? So particles don't have to come close together. This will cool the neutron star very fast, but it'll only cool heavy neutron stars very fast because of this requirement. Modified Urquhart process, where you have two nucleons going instead of just one isolated nucleon, that relaxes the restriction on energy and momentum conservation, and it gives you another cooling process that will work throughout the whole core of the neutron star, but it's much slower being a two-body process. The superfluidity, I mentioned that in neutron matter and S-wave superfluidity. It's also very important in neutron star cooling, but it's mostly in this 3p2, 3f2 pairing. The neutron matter in the neutron star is so dense that the S-wave pairing is already gone, the density is too high, the interaction is repulsive, but the interaction is still attractive in this 3p2, 3f2 channel. So that means a triplet pairing, two neutrons with the same spin, and because by anti-symmetry they have to be in an odd parity wave, and triplet P2 is the lowest. These two angular momentum coupled to J equals 2 is the lowest or most attractive channel. So that's expected to make a significant difference in the cooling. Why that matters is because if you have this pairing, the single particle states are not available. You have this gap, and so that restricts the phase space quite a bit, and that can change the cooling a lot. The triplet P2 gap is a lot smaller than the S-wave gap. It's very uncertain. Microscopic calculations are not as good. The interaction is a little less well known. But if you take sort of typical values, you can see quite a big dependence on the gap. There's a nice review paper on this by Gazerlis, Pethek, and Schwenk just a few months ago. So I think this is a very active topic of current research, neutrinos in very cold matter relevant to neutron stars. It has to do with equation of state. The neutrino emission and propagation also has to do with superfluidity. The protons can also be superfluid, even if you only have 10% of them. They can pair up, and that can have an impact. Similarly, if you look at earlier times when the neutron star is still very hot, then you have to look at finite temperature calculations. In these systems, the neutrons and protons are essentially degenerate. You're filling up Fermi spheres. But in the supernova regime, at the end of the neutron star, the temperatures can be quite important, and it's really a non-degenerate matter problem. That's more difficult, but I think it's very likely that the nuclear interactions are extremely important here too. And one of the things we're interested in looking at is the weak response of matter, neutrino propagation, and what are the spectra coming off of the protoneutron star. There's a lot of progress in theory. There's even more progress in observations, these two solar mass neutron stars, the mass radius relations, terrestrial experiments on neutron matter, and also on related things like cold atoms. So I think this is a very exciting topic. It's connected through the neutrino physics to a lot of the other things you've been hearing about. This is what's basically giving you the initial conditions on the neutrino oscillation. And as I hope I've showed, there's a lot of connections. to condensed matter physics, astrophysical observations, and one of the most exciting things is the studies of gravitational waves, which we hope to have signals in the next few years. Let me stop there. Thanks. Yeah.
How many observations do you think you would need of high precision mass and radius for neutron stars before you're really satisfied you'd efficiently probe the parameter space?
Yeah, well, I'm kind of confident, especially very confident at the low density. Let me try to find a mass radius relation here. Yeah, so one of the graphs I showed you had all kinds of mass radius relations doing all kinds of weird things out here. I just don't think that's very credible because the energies per particle at these low mass neutron stars are only like 20 MeV. So only changing a neutron energy by about 20 or 30 MeV compared to its rest mass. So I think this part of the curve, according to me, is extremely well constrained. You know, you'd have to have something totally exotic, like a very low density phase of quark matter. I just don't think that's very credible. So if you had a couple of points, if you knew the mass and radius of a 2 solar mass neutron star, that would be extremely constraining if you believe this low density stuff that I say. So basically, it can't be too far away from vertical, just because if you're this far in, if it's so attractive at low density, and you're going to get a 2 solar mass neutron star, there are constraints from causality and things that say that you have to be essentially vertical. So you really don't need a lot, but it's very important to have some high solar mass neutron stars for that constraint.